Alright. So our task is to do the ratio and root tests and interval of convergence today. So the ratio and the root test both have some of the same parts. They also follow the same rules, which is nice. And they're sort of related to the comparison tests. The only difference is we're not creating the other series. The series that we're using, we're just going to do a sub n, and then we're going to plug in n plus 1 into that series to get our other piece that we want. So we have to have the limit as n approaches infinity. We have to have an absolute value, an plus 1 over an. And all three cases, we get some number out of it. If that number is less than 1, converge. If it's greater than 1, diverge. And if it's equal to 1, we can't do any more. So let me try a few of these and see if they make sense. So I've got negative 3 to the n over n factorial. So first thing is I need a limit. How's that red show up? Okay, I guess. Probably not the best choice. I need absolute value. I need this whole term, but to n plus 1. Then I'm going to multiply, instead of dividing, I'm going to multiply by the reciprocal. And then close this up. Now, before I continue, I wanted to do a quick review of factorials because I'm not sure how many of you are familiar with them. So first off, if I said 5 factorial, well, that means 5 times 4 times 3 times 2 times 1. And 3 factorial is equal to 3 times 2 times 1. So if I wanted, I could write 5 factorial in terms of 3 factorial. It would be 5 times 4 times 3 factorial. So basically I can stop anywhere along this line and put a factorial. Right, so that would also be 5 times 4 factorial, for instance. Another strange thing about factorials is 0 factorial is actually equal to 1. That's by definition. I don't remember the proof off the top of my head. You can look that up if you're really interested. And then another thing I wanted you to notice is to get, say, from, or if you have 5 factorial, right, this is 5 times the next number, which is this number minus 1, then that number minus 2. So, for instance, if we had n factorial, that's n times n minus 1 times n minus 2, and so on. We could stop and just call that factorial. If we had n minus 1 to start with, that would be n minus 1 times n minus 2 times n minus 3, and so on. And if we had something like n plus 1, well, that would be n plus 1 times n factorial. Because we always take away 1 from the inside. So any questions about factorials before I continue? All right. So if I want to continue here, I need to start breaking this down. So this is negative 3 to the n times negative 3 to the 1 times n factorial. I leave that one alone because I have n plus 1, which I know if I break that up is n plus 1 times n factorial. And then on the bottom we have negative 3 to the n. So we can go ahead and cancel the negative 3 to the n's. And we can cancel the n factorial. Then I've got an absolute value, and I've got a negative 3. So the absolute value of a negative number makes it positive. There is no way for n plus 1 to be negative. Right? N starts at 1 and runs to infinity. So I can take the absolute value away and make that negative 3 a positive 3. I'm left with this. If I plug infinity in there, this goes to 0. That number is less than 1. Therefore, by the ratio test, this converges. So if we're good with that one, I'll go ahead and start the next one. Isn't it diverges? So let me scroll back up. So I figure out where my mouse is. There we go. So see here it says if L is less than 1, converge. So I think maybe you were just confusing it with one of the other tests that we've done. Okay. So let's do this one. Same thing. Take the limit. N approaches infinity. Absolute value. Everywhere I see an n, make it n plus 1. Then multiply by the reciprocal. Now this 2 to the n plus 1 is really 2 to the n times 2. So this 2 to the n cancels with that n and leaves behind just 2. And that 2 has nothing to do with the limit, and it's positive. So I'm going to pull it all the way out in front. Left behind I have n plus 1 divided by n all to the 200th power. And again, no way for n to be negative, so I just dropped the absolute value at that point. I'm going to rewrite the inside here. Like that. And then if I take the limit, the 1 over n portion goes to 0. I get 1 to the 200th power, which is just 1. Again, less than 1. So converges. Any questions about that problem? All right. So that's cosine n pi and then the third root of n plus 1. So, what kind of series are we looking at here? Yes, it is the third root. Right, this is an alternating series. Good. So, some things that make the ratio and root tests useful. If there is an alternating part, you can either use the alternating series, or most times you can use the ratio or the root test. The ratio test is most useful when there's an n factorial. So if you see any kind of factorials in there of n or n plus 1, then that's a good indicator that you should be using ratio test. So again, limit n approaches infinity, absolute value. Everywhere I see an n, make it an n plus 1. This is n plus 1 already, so it becomes n plus 2 in there. And then multiply by the reciprocal of the original. All right, now cosine n pi and cosine n plus 1 pi will both alternate. So if I take the absolute value, these cosine terms will disappear. I can also get rid of 3 to the n and that n right there, leaving me with the 1/3. So I'm going to pull the 1/3 out in front. Still have the limit as n approaches infinity. Can you explain why? Sorry, I'm in the way here. Can you explain why? Oh, great! Now the box is in the way. Let me just look on my phone. Can you explain why this indicates a good ratio test again? So this one, just because it's a very complicated alternating series with a lot of n's, is probably a good choice to use the ratio test. But the best indicator that it's useful is a factorial of n. So I took the 1/3 out. These cosines are going to disappear when I get rid of the absolutes. The n's have no way of becoming negative. So I can get rid of the absolutes and they stay. And then I'm going to go ahead and put the cubed root portions together and the squared portions together. So 1 cubed root of n plus 2 over n plus 1. And then I'll have 1 squared term, which will be n over n plus 1. No problem? And then each side, or inside of each of these, I'm going to divide every single term by n. So now, if I take this limit, anything divided by n goes to 0. So 0, 0, that means this is cubed root of 1. And this is 1 squared. All of which just going to give us 1. All times 1/3. That's less than 1, so we converge. Is dividing by n and the cubed root any different? If I do it inside, then no. If I try to start outside and introduce it on the inside, that's different than if I just divide every single term inside by n. Right, effectively I'm multiplying top and bottom of the fraction by 1 over n, and there's no reason I can't do that. All right. Do you guys need a few seconds to copy that down? All right, I'll wait a minute. Not sure why you're saying sorry. There was nothing that came before it. You mean you need some more time? How did we cancel the cosine n pi? Or n plus 1 pi. So n pi, right, that we know is alternating. You would get cosine pi, cosine 2 pi, 3 pi, 4 pi, right? Well, what about cosine n plus 1 pi? Well, that's just going to be the same thing, but it's going to start at 2 pi, and then 3 pi, and 4 pi, and 5 pi. Right, so it's still alternating. All right, are we good? Where in the world is the mouse? There we go. Refocus. There we go. All right. Last one. So again, there's that n factorial. That should be a clue that ratio test is a good idea. So limit n approaches infinity, absolute value, n plus 1 to the n plus 1 over n plus 1 factorial. That's making all of these n's n plus 1. Multiply by the reciprocal. So you might look at this at first and go, uh-oh, these aren't going to cancel. But we're okay. This n plus 1 factorial is the thing that we have to reduce. Because if we tried to reduce this one, we'd get down to n minus 1. That's not going to cancel. But this one will go from n plus 1 to n factorial. So let's write that down. So now notice we have n factorial over n factorial. And this n plus 1 can cancel with this n plus 1 to the first power. Right, if you needed to, you could write this out. This is n plus 1 to the n times n plus 1. And that's how I canceled the n plus 1s. That leaves me with this. Right, there is n plus 1 to the n divided by n to the n. That's all to the n power, so I can put it all together as one fraction. And if I rewrite this, I'd like you to tell me if you recognize it. Does anyone recognize that limit? So it has 1 over n in it, yes, but it is not quite the harmonic series. You're close. It is exponential. Anybody else want to give it a shot? In this case, the absolute value disappears because there's no way for any of the values of n to be negative. So there's no need for an absolute. Alright, so since we didn't get it, let's solve for it really quick. I'm going to call this y. I'm going to take the natural log of both sides. Remember, the natural log can go inside the limit and vice versa. That allows me to bring this n down in front. And here's where it's strange. Instead of writing n, I'm going to rewrite that as divide by 1 over n. Because this is L'Hopital's rule here. If I try to substitute, I get natural log of 1, which is 0, and 1 over infinity, which is 0. That tells me to use L'Hopital's rule. So derivative of this is 1 over the inside, divide by the, or sorry, times the derivative of the inside. And then you get the same thing down here. So this is that. Plug in infinity, get 1. But remember, this equals natural log of the thing that we wanted. So if that's natural log y, we've got to take e of both sides. And so y equals e. So that's the definition of e, this limit. So you may have seen that in Calc 1. But that's the proof. Questions about that one? I know that's a lot of work there. Yes, this diverges, right? If the limit comes to something that is greater than 1, it diverges. How did we get the n factorial in the denominator? So n plus 1 factorial. Right, you're talking about this, I'm assuming. So n plus 1 factorial is equal to n plus 1. Then you take that number minus 1 factorial. But those cancel and you just get n factorial. And so yeah, this is greater than 1, so diverges. Let's go with that one. Okay. So I believe those are all the examples I had for you for the ratio test, which means we can start the root test. So the root test is nice because it follows the same rules. Less than 1 converge, greater than 1 diverge, equal to 1 inconclusive. So that's great. It also still has a limit. It also still has an absolute. The difference is now we have the nth root and we just need a sub n. So let's try the first one. Limit n approaches infinity. Nth root of the absolute value of this entire term. Now, the question is, can we get rid of the absolute? Well, the top here is always positive because n starts at 1 and I'm adding and multiplying there by positive numbers. So if n is 1 in the denominator, we get 6 minus 5, which is a positive number, and anything above that will be positive. So right off the bat, we can get rid of the absolutes. And therefore, we've got the nth root of all this stuff to the n. So that cancels. So we have that. And if we want to solve that, then the best thing we can do is probably divide everything there by power, highest power of n in the denominator, which is n squared. So by doing that, then applying the limit, this and this will go to 0. And I'm left with 5/6, which is a number less than 1. So converge by root test. Give you guys a second to copy that down if you need. All right. So the ratio test was good to use when we have n factorials. The root test is going to be good to use when everything is to the power n. If there's something that is not already to the power n, we're going to have to use that log process that we did for the previous problem. All right. So once again, I want limit n approaches infinity, nth root, plug in a sub n, and then we need the absolute value of this. So the absolute value here is going to make this -1 to the n back into a 1. Right, because -1 to the n alternates, but the absolute value makes it a 1. And in fact, we're allowed to write 1 as 1 to the n. Then I've got the nth root of two things to the power n. Again, you may not recall arctan or how it what it does out at infinity. So if you remember this graph of arctan, remember that it's got an asymptote up here, and it is pi over 2. So at infinity, it goes to pi over 2, which means this is 1 over that, or 2 over pi, and that number is less than 1. Any questions about that, guys? Couldn't the whole fraction be to the nth power? So yes, you could write it as all to the nth power, but I decided to get rid of the -1 to the n with the absolute first. So technically, arctan, when n is 1, right, is just that portion. So it's always positive. But -1 to the n necessarily is not. So we couldn't get rid of the absolute until we did that. Why is the arctan n pi, or arctan of n, equal to pi over 2? So that's just by the graph, right? Arctan gives you this curve here, and it is bounded by two asymptotes, which are pi over 2 and negative pi over 2. Okay, we go with that one. Okay. So notice this one here, and this 3, it's a third root, not n cubed, by the way. I need to space it out. So notice everything there is not to the n power. So root test might not be the obvious choice, but most of it is. So we can still use it. So that's the limit n approaches infinity, nth root of n times, now I'm going to rewrite this as 4 to the n over 3 all over 7 to the n. I can then rewrite that again. Nth root n times, I'm going to rewrite it as the third root of 4 over 7 to the n. So when I take the nth root, this will cancel, but this n will still be to the nth root. And this is just a constant which can be pulled out in front. So I pull that out. Then I've got the limit as n approaches infinity of n to the 1 over n, right? That's the same thing as the nth root. Any questions from how I got from here to here? Okay. So now, if you try to apply the limit, you get infinity to the 0. That is one of the forms that say L'Hopital's rule can be used, but you've got to rewrite it first. So once again, I'm going to let this whole thing equal y. Take the natural log of y. Actually, in this case, I'm going to let this equal y, because I don't want to deal with that number out in front. So you get that. If you take natural log of n to the 1 over n, you bring the 1 over n down, and you still have natural log. But instead of writing it this way, I really want to make it natural log over n. And the reason is, if I now plug in, I get infinity over infinity, which says go ahead and use L'Hopital's rule now. So that's limit n approaches infinity. Derivative of natural log, 1 over n. Derivative of n is 1. Limit of 1 over n is 0. But this is equal to the natural log of y. So we have to take e of both sides, which means y is 1. So this limit here is 1 times this constant. So you get that for the entire limit. And that number is less than 1. Questions about that guy? So we're all good then? All right. So that was the root test. We can now do power series and their interval of convergence. So of all the topics that we cover for series, this is probably one of my favorites. Now, not necessarily the interval of convergence, but power series in general. Power series are great. They allow us to solve a lot of problems that are too tough to solve. So a power series is going to be a polynomial, and it's going to be a summation, right? So any power series can be written in this form. So here's an example. They gave us e to the x. And you'll hear me a lot say this is called a power series expansion. So this is an approximation to e to the x. So e to the x to the first 5 terms looks like this. And that can be written as a summation that looks like this. And we'll prove this later. So if it looks like this form, this c sub n, that's just some constant. And in this case, it's 1 over n factorial. So as you see here, it says almost every computer algebra program, graphing calculator, and online application uses some form of infinite series, and most of them power series, to model transcendental functions. So what's a transcendental function? Something like that. Write an equation where you can't just get x equals out of it. So instead you could plug in the polynomial functions for each one of these to approximate it. So power series are great, but they're only great if they converge, because if they don't converge, there's no point in using them. So the question is, where do they converge? Well, they converge between -1 and 1 for the value of x. And that really means absolute value of x less than 1, or convergence. Where have we seen something like that recently? Any suggestions? Any thoughts? So when I say something looks like that, I'm saying absolute value of something, and we get less than 1 for convergence. I'll give you a hint. Maybe read the next line in the paragraph below. Still no suggestions? Hey, there we go. Ratio and root tests, right? We just got done doing those. So, if I want to test the interval of convergence, I'm going to use the ratio or the root. Now I'm going to skip this one and come back to it because it's got a strange answer. And I want to actually solve one of them first. So let's do this guy first. Alright. Now in all the examples I've given you, the ratio test is going to be the better choice. Right, we do have something to the power n here, but this isn't, which means we'd have to use that log stuff. That's no fun. So let's try the ratio test. So we need absolute value. I need to take this guy to the n plus 1, multiply by the reciprocal of the original. And I need this to be less than 1 for convergence. All right. So I've got 3x minus 1 to the n plus 1 and 3x minus 1 to the n. This will cancel with the power n up there. We know from previous problems that the n has no way of being negative, right, if it starts at 1. So these two things can come out of the absolute value, but must remain within the limit. So we have that. And then we've still got this 3x minus 1 to the first power left over. There is a possibility for it to be negative. So it must remain inside the absolute. It, however, does not have any ends, so it can be pulled out in front. So now we need to contend with this limit first. So instead of n over n plus 1, rewrite the limit. And again, still less than 1 required. So I divided everything in there by n. So this whole limit, right, all of this equals 1. So there's nothing really new there, except now I'm down to here. Now if I've got an absolute value that's less than 1, that means whatever's inside the absolute could fall anywhere between -1 and 1. And I'm unsure as to how familiar or how much you remember inequalities. So if I want to get x by itself, I got to do some operations. But if I do an operation, I've got to do it to all three pieces. So I'm going to add 1 everywhere. And then divide by 3. So this is my interval from 0 to 2/3. But I've got to go further than that. I have to test both endpoints. Because I need to know, could this be equal and could this be equal? So to test the endpoints, I need to take them and plug them back in to my original sum. I then need to test whatever I get out of that. So let's say left, for left endpoint. Plug 0 into the original sum. If I do that, I get -1 to the n over the cubed root of n. What kind of series is that? That is an alternating series. Good. So with an alternating series, I need to prove that it's decreasing, and then I need to take the limit of the absolute value of a sub n. So that plot looks something like this. It's decreasing. And I know every one of these that I do basically looks like that, but please, when it does come time for you to do one, actually plot it and make sure it looks exactly like that before you draw it. Then I need the limit as n approaches infinity of 1 over n to the 1/3. Well, that goes to 0. That meets both criteria for the alternating series. So if this converges, it's equal to that endpoint. All right, now I need to do the right endpoint. So I need to plug in 2/3 into the original. If I do that, I get 2 minus 1 to the n. Well, that's just 1. And 1 to the n I can just write as 1. So what kind of series is that? Very good. That's a p-series. So in this case, p is 1/3. That is less than 1. What does that mean? Good, diverges. If that series diverges, it is not included. So I'm done. My interval of convergence is 0 to 2/3. Any questions about that problem? I know there's a lot. And I want to point out the one thing that students do every semester that I don't quite understand is that they know to test the left and right endpoints, at least the majority of them. But when they do that, they just automatically take the limit. And I don't know why. I guess they assume that because they used the ratio or root test to begin with, that's how you should test the endpoints. But it all depends on what kind of series they are. So the left endpoint here was alternating, so yeah, we did need to take the limit. But the right side was a p-series, so all we had to do was just say it's a p-series and determine if it converged or diverged. Yes, that interval that I gave there is the final answer. So what does that mean? That says that the series that's given there only works, only converges if x is some number between 0, including 0, up to 2/3. Any numbers outside that range, that series does not converge, and it's basically of no use to us. We ready to move on to the next one? Okay. All right. 4x plus 3 to the n over n times 2 to the n. So again, you could use root test here if you wanted, but I'm going to use the ratio. So I start there, right? I take all the n's here and make them n plus 1, and I multiply by the reciprocal, take the limit, and all of this has to be less than 1. So now I need to cancel as much as I possibly can. So I see a 2 to the n, that will cancel with an n right there. And the same thing happens for this n, everything to power n, and that n. Again, I've got 4x plus 3 to the 1 power, which must remain in the absolute values. But it can come out in front. And I've also got to divide by 2 here. So that's going to come out as well. All right, I've got 4x plus 3 over 2. Limit, n approaches infinity. And I've got n over n plus 1 left behind. And this whole thing must be less than 1. Okay. Again, if we divide everything here by 1, or by n, sorry, by n, we get that. And so this whole limit here is equal to 1. So we've now got the absolute value less than 1. If the absolute value is less than 1, everything in there must fall between -1 and 1. then do your manipulation there. So I'm going to multiply through by 2. Subtract 3 everywhere. And then finally divide by 4. So that's my interval. I just have to find out what happens at the endpoints. So the left, plugging in minus 5/4 right there. Doing that, 4's cancel, and I've got minus 5 plus 3, that's negative 2 to the n. So then I've got negative 2 to the n over 2 to the n. That turns out to be negative 1 to the n. Again, this is an alternating series. Got to prove it's decreasing. I know 1 over n is decreasing. It looks something like that. Then I need the limit as n approaches infinity of the absolute value, which means the negative 1 to the n disappears. And that is very easily 0. So we meet both the criteria. That becomes equal to. Finally, we need to do the right endpoint. So that's plugging negative 1/4 back in there. So this is sum. 4 times a negative 1/4 is going to be negative 1 plus 3 to the n over n times 2 to the n. Negative 1 plus 3 is 2. So we end up with 2 to the n over n times 2 to the n. These cancel. That leaves me with the sum of 1 over n. Can someone please tell me what that is? Good, that is the harmonic series. And because of that, we should know automatically diverges, which means that is not included. So my answer to this problem is minus 5/4 to minus 1/4. And that is my interval of convergence. So I'll leave it there for just a minute in case you need some time to copy. And then I'll go back and finish the very first problem in this section. And then we'll be done. Alrighty. So like I said, let me go back and finish up that first problem. All right. So x to the n times n minus 1 factorial. Take the limit. N approaches infinity. X to the n plus 1. N plus 1 in here. We've already got a minus 1 in there. Just becomes n. And then we would divide by the original. We'll have to reduce n factorial. So x to the n cancels. N minus 1 factorial cancels. And I've got limit n approaches infinity of n. Now here I've got absolute value of x, and all this has to be less than 1. So how in the world can I make this less than 1? Well, if I evaluate the limit first, let me rewrite that out infinity symbol. Right, the limit as n goes to infinity of n. Well, that's just going to blow up and go to infinity. So there's nothing I can multiply that by to get less than 1, except for if I plugged in x first. What's the only value of x I could plug in there? Well, 0. So this one's really weird. That is the interval of convergence. That's why I don't like to start with that one. Any questions, guys, before I cut off the recording? Can I explain that again? Which part? The very last part? So if you look at it again, right, we've got absolute value of x. We've got limit of n, or n approaching infinity of n. I said if we plug in x first, what's the only way to make a number less than 1 if this number could be anything. It would be to plug in 0, right? Alright, so I'm going to stop the recording.